Hey, what's up, guys? Yeah, so previously I discussed the solvable groups, but I haven't discussed example. So I want to make a very short video discuss some examples which are solvable. Okay, so originally we proved that the G is Pn if prime power n is solvable, and G is abelian, then G is solvable. Okay, and there are some, and we proved that Sn and greater or equal to 5 is not solvable. Okay, so how about others? This is not a simple task. Okay, so for example, let's consider S3, which is a triangle, right? So which is a triangle, and obviously that it has a normal subgroup A3, and this is Z2, and this is Z3, so it's abelian, so this is solvable. Okay, so S3 is solvable. So in the Galois theory, that if you give me an irreducible cubic equation, then your Galois group is bounded by 6, right? So the group with order less or equal to 6 must be solvable. Okay, and the fact is that S4 is solvable. Okay, so this is also a common technique that you can, by definition, there a symmetric group with this alternating group is a normal subgroup of S4, and then this is abelian because this is order 2, and then this is V, which is a Klein group. You can check this is identity, and 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And so once you know that this is Klein group, you know that this is Z2, Z2, so it must be solvable because these guys are abelian. Okay, so in this is why in the Galois theory, if you give me a quartic equation, the degree f is 4, then your Galois group of this will be the subgroup of S4, and so S4 is solvable, so every subgroup of a solvable group is solvable. So which proves that in the quartic equation, your Galois group is also solvable. So Galois group of quartic is solvable. Okay, and some other there are another two cases I want to say. So for example, the dihedral group is solvable. Okay, so that dn should be written as I think usually people like to, I think it's R and S, which is R to the n is identity, and the S squared is identity, and the SR S inverse is R inverse. Okay, so you can view it's basically the polygon, an regular polygon. So you get the, let's say this is n regular, let's say n is 5, and you get the n polygon, and the S is a rotation, S is a reflection, and R is a rotation. Okay, so obviously that Dn contains the normal subgroup which is generated by R. So this is isomorphic to Zn, and then this is order 2, so this is Z2, so this is normal, and then this is abelian, so you can directly go to identity. So this proves that the dihedral group is solvable. Okay, another final results I want to say is this famous Q8, or the quaternion group, is solvable. So quaternion group contains 1 I, j, k, and then -1 minus I minus j minus k, and which satisfy the ij equals to k, kj equals jk equals I, ki equals to j, and ji is minus k, kj is minus I, and the ik is minus j. Okay, so QA is solvable. Okay, so this is a very simple exercise, but basically QA contains, you can take the subgroup like plus or minus I, right? So, is it? Sorry, it's a, you can take a subgroup generated by I. Okay, so basically I should say generated by I. So this is 1 and 1 and I and I squared, which is -1, and I cubed, which is minus I. Okay, so this you can prove that this group is normal. So you actually don't need to prove it, right? Because it is order 4. So this is this order 2, right? So this order 2 that means that it must be Z2. So for the order half normal subgroup must be normal. So this I must be normal, and right. So and then this is a cyclic group, right? So you can directly go to identity. Okay. So that's it. So basically, we prove the S3, S4, and the dihedral group, and this QA group is solved. Okay, see you guys next videos.